we'll move on to our next presentation. This is from Shuzhao Li from the Jackson Laboratory, Mummichog 3, Aligning Mass Spectrometry Data to Biological Networks.
All right, so can you guys see my slide correctly?
It looks good and you sound good too.
All right, thank you. Yeah, I'm Shuzhao Li. So my lab is actually in Connecticut. So we are on the new campus of Jackson Laboratory. My co-PIs are Jeff Xia and McGill, Gary Suzak at Scripps. So this will be a joint presentation by the three of us. Our project has a title, Mummichog 3, Aligning Mass Spectrometry Data to Biological Networks. But after 4 years hard work, we thought this might be a more appropriate title for today, how to navigate metabolomics through the data lakes and the informatic cloud. So the Mummichog software was first published almost 9 years ago because I had this burning problem in my own research project, how to do pathway analysis when metabolite annotation is uncertain. So we are doing much better today in terms of metabolite identification annotation, but the problem still exists for many metabolites, and the situation is not going to change anytime soon. The idea of Mummichog is to look for connection patterns in known biochemical reactions based on predicted metabolites, then prioritize the hypothesis of pathway enrichment. So Mummichog was integrated into XMS Online by Gary's lab in 2015. Since then, we have had a series of milestones listed on the right. So here, actually, I would like to give the podium to Jeff to talk about the work related to metabolic analyst before I continue with the Mummichog Cloud project. So Jeff, you can speak at our advance the slide for you.
Okay, hello everyone, and thank you, Shuzhao. So the first is, I echo Shuzhao's comment about the metabolite identification, which is quite an obstacle. So, so my team, our team, Shuzhao, me, and Gary, we both have access to equipment. We are also doing a lot of computation. So one of our shared passion is how we actually can democratize the metabolomics, just like other omics, and in terms of experimental cost, computing cost, and intellectually, how much satisfying biological story we can get from that. So for this project, and we are focusing more computationally how we do that. So my group developed Metabolomics. So early days, all the early versions, we all focus on on-target metabolomics, which is just a concentration table. We can easily map in the compounds to the database and doing stats and doing functional analysis. Seems more or less done. But the field is quickly moving to on-target metabolomics. A lot more we can get from that. But how we can get more from this on-target metabolomics, and which is robust and high throughput. And it's identification being quite an issue, because that's really scare a lot of people who is not in the field, and also quite uncomfortable how to do it in a large scale. And actually, we recently just doing just simulated study and see how much we need to identify within the metabolomic data, like the whole, to get a good story out. And we actually found out like from 5% all the way to 100%, up to like 20-25%, the biological story in terms of the pathway stuff is almost not too much increase. One reason we think is that there's a lot of redundancy in our metabolomics data, and we don't need to really get everything out. And so using a redundancy, we can actually robustly get the stories out. And I think this is one of the key strengths of Mummichog. And this approach we implemented on MetaboAnalyst, and since last 12, and it's also linked to Gary's XCMS. And so over the last 12 months, we actually processed more than 115,000 jobs. And this is just for functional analysis. But if we're really talking about the stats, then probably much more. Shuzhao, can you move on? So the underlying all the pipelines based on XCMS, and we also did one wrapper around XCMS. It's called OptiLCMS, and moved to Mummichock. One thing is that XCMS is really powerful and versatile, and but we soon realized that the addressing parameter get optimal result became quite a bottleneck. If we put it on a web and let people who's not expert in the field to do it, it's really hard for them. And also a lot of errors make people cannot go through and send us emails. So it's, so to address that, we developed a package called OptiLCMS. Basically, we focus on the like pull the sample, the spectrum, focus on the regions that contain a lot of signals, use that to really train our optimization algorithm, and which then apply back to XCMS. So it takes about 10 to 20 minutes, we can get a much better result. And the result can send to Mummichock to do a functional enrichment analysis. And because there's a lot of the changes and the updates and the things, we almost do a benchmarking every several months. So this is on the left side is what we did last year, and this is what we did in March this year. So overall, that we see that with just 10 or 20 minutes extra, we can get a better result in terms of the annotations and get the biological, like say, internal variance explained and potential compounds being annotated. So this is all MS1. We haven't go to MS2 yet, but overall that we see the optimization step significantly improve the pipeline, and we seldom receive the complaints after we get this kind of wrapper there. So user can almost default, they will choose the optimized approach, they just go through the whole thing. And Shuzhao, can you move to next? So one of the key kind of component for Mummichock to working properly is you need to define a groups of metabolites, like call it metabolite set, and for the redundancy to be picked up by this algorithm to get the stories out. And our group actually expanded almost 10 times in the last several years by incorporating pathways from other databases, from other species. And more recently, we incorporate a lot of the lipid maps and the RefMat. And so we have about 2,500 metabolite set. But just today, we have another paper just accepted for MGUS study. We have manually curated 65 MGUS study. So it contains like a genetic informed metabolite type. So if we involve this one, if we're probably going to add it in the coming weeks, we probably double or triple the metabolite sets. Basically, it's all SNPs or genes associated metabolites based on statistical cutoff. So I hope with this more adding, we can have a very rich stories for the researchers. Like there's a tool called EnrichR, which have almost millions of metabolite sets, and it seems quite useful. And but here, as I think we can continue adding it, and to help users to have different interests. Yeah, can I move on? And so for Mummichock, the original defined input is a ranked LCMS pick list. You can have this p-values or MZ and potentially retention time. And this is very well defined. So the user, when user use this defined pick list, what try to tell is that the significant pick list are enriched for certain functions. And so this is clearly this is primary interest for a lot. But when we actually get the data and have a huge tables of expression from intensity tables, and we want to get almost same thing like what we want to get from gene expression table. And here is a heat map from the peak intensity table uploaded by the users. And if we do some cluster analysis, you can see a lot of peaks clustered nicely. And in this left side, you can select on top. You see there's a control versus disease is upregulated, and down there's another pattern. Actually, the other side is opposite, so it's more enriched from the left and downregulated in the other side. So you can combine the signatures and have a patterns and test it. You run Metabolomics on top. So this is only possible. You have a GUI and interactive. So you just drag and select to do it. So this is really stretch your mind, because a lot of people just really naturally want to click around and think and have a hypothesis. So this one is we spend a lot of time is mainly just JavaScripting, but overall the feels a lot of users use these tools, these functions. On the right side is we use Metabolomics to do COVID meta-analysis. So this one was published last year for our round 1 and COVID-19 meta-analysis from basically this is a seven data set. That's January last year, and we use Metabolomics. We can actually detect more consistent pathways that across different studies also sees some differences. And so this one, some patterns very striking. And if we go to see their PCAs individually, there's a lot of the things we can consider. Right now, we are doing a round 2 COVID-19 because now it's almost the end. And all the data, so far we collected about 65 studies. There's no much increase, seems quite stable. And we do a round 2 and see how much conclusions will be the same or news. And Zhiqiang, which will give, Zhiqiang, my student, will give a lightning talk probably Thursday on the new analysis with this 65 data. Can I move to next? So this one actually shows a glimpse of the kind of COVID-19 data, just a subset of probably just 5. We talk about 65, but the purpose is not for COVID-19 data. Actually, it's on the algorithm of Metabolomics itself. And the motivation behind this is that we use Metabolomics a lot. We found it's quite effective, but on the other hand, we also doing a lot of the enrichment analysis from other omics field like gene expression. They use GSEA and quite a lot. We're also doing overrepresentation a lot. And all this algorithm very popular, and they accept a ranked list to do the enrichment analysis. And we really just wondering how this algorithm works. And well, if we adapt the initial fuzzy mapping step, can it work as well or better? And so we actually did a very comprehensive simulation using both just imagine different scenarios, also use the real data. And it turned out its Metabolomics very robust and sensitive. I figure is that because the metabolomics data in terms of the fuzzy annotations and incomplete background, and Metabolomics need to do a lot of the defensive programming to address the bias, potential bias. So overall, that it's very consistent, outperforming in a lot of the recall, precision, and several other things. So it's very satisfactory. We see it perform very well. And yeah, there's also some other potential things we noted we could slightly improve. And this is one of the lightning talk from Yao, she's going to present tomorrow. Thank you.
All right, thank you, Jeff. So in order to convert Metabolomics, who started as a standalone command line tool to an enterprise level product that is robust, easy to use, and to cater to a very broad range of users. It takes actually a lot of new design. That's how we came up with this cloud project for Metabolomics 3. So one of the reasons to use cloud is that we cannot afford a local system administrators. So probably more important reason is that we want to be able to focus on software and algorithm development, not on the sheet metals. So the cloud project is led by Francisco and Yorgi, two very talented software engineers at the Jackson Lab. So if users come to our front end website, that's upper left side, so users submit the jobs, then there is a back end web application framework to cache the data and notify a downstream system that is a message queuing system. It is really like a shift manager. So when the manager sees new jobs posted by users, then the manager calls up workers. So a worker here on the top right side is really the Metabolomics package equipped with a bunch of communication tools. So the manager calls the worker comes up and does the job, and then after the job is finished, the user is notified and direct to the result. So if there is a large number of jobs submitted, then the manager can simply just call up more workers, or these are identical clones, and there is no labor union, so productivity is guaranteed. That's how the system can scale up to very large demands. So there are a lot of the technical details behind this, which is really a separate discussion. So I want to show you a quick screenshot of the current server. So the test server of Metabolomics 3 is running and open to the public. So after a job is finished, users are directed to the result page. So this is part of the result page on a significant network module. So if you were on a live system, you can actually hover or click on any of the nodes and it will bring up the related information. So because the data are complex, so this type of interactive visualization is really important and useful. So the consequence of being modular is that Metabolomics grew from a single package to a whole family of libraries. The screenshot you saw at the front UI, it is what we call math browser, and most of the cloud components are in the API package. Then the Metabolomics 3 core package has the algorithm to do actually the scientific calculation, which is supported by infrastructure of a database. Annotation is separate now. It's going through a JMS package. Then low-level calculation of chemistry and mass spectrometry is in the MasterChem package. So in order to effectively communicate between different components, we rely heavily on JSON format for data exchange. So this is just a quick example of how the data look like when they are exchanged between different components of Metabolomics or between Metabolomics and other software tools. End user don't really see this a lot, but for a good computational project, the data models are really the foundation, the backbone. So we spend a lot of time to design, to write examples on this. So this is a quick overview of the key concept, key models in everything, almost everything we do. So on the right side, so these are the concepts around metabolic models, reactions, pathways, networks. On the left side, that's how we model the experimental data from metabolomics. Then experimental data in metabolomics are annotated into imperial compounds, which are really the key to connect probabilistic annotation with theoretical compounds. So the code is in Python, JSON, and YAML. So all of these are open on GitHub. We encourage people to reuse them, modify them. So we all know that metabolomic data do not start with the pathway analysis or annotation. Actually, annotation has to be part of data processing. So we also wrote a completely new tool for data processing called Asari. Amanda Sadiq is going to talk about the Asari project tomorrow in her lightning talk. So Mike mentioned something earlier that he saw epidemiological studies of tens of thousands samples. So I'm going to give away one piece of information here. Asari is very fast, a lot faster than any other tools. So if you have tens of thousands samples, Asari has the performance to actually get the job done. There is a variant called Xari, which will be in the presentation by the Emory CIDC group tomorrow. So before I switch to Gary, so let me quickly acknowledge the generous support by NIH and by the Jackson Laboratory. So this is our campus in Connecticut. So our group also have 6 lightning talks. Gary will talk more about methylene this afternoon. Yo will talk about pathway enrichment. Amanda will talk about a theory for data processing. Mahisur has a application project on ectoderm differentiation. So Ziqiang will talk about COVID metabolomics, and Minho will talk about JMS, the annotation package to bridge genome scale models and metabolomics. So I'm going to stop sharing, and Gary, you are on.
Can you see my screen?
Yes.
Ah, great. Sorry about that. And I trust you're seeing the screen that.
Yeah, your presentation's up now, Gary. Thanks.
Okay. How about now?
Now we see the presenter view where you're reviewing the next slide. It was okay, but then switched it.
Okay, great. Okay, so Shuzhao and Jeff gave a very nice presentation on how the mummy-chog has been his latest developments in mummy-chog, and one of my relatively small role in this project has been to implement some of their changes or improvements into XCMS, and we're currently completely rewriting XCMS. We're actually in the alpha stage of testing it right now, and we're calling it XCMS Gen 2. And instead of going through the different things that we've tried to accomplish over the last 5 years or so, I've decided that I'll just do that in a lightning talk and instead focus in on what I find the most interesting part of what's currently going on and coming out of this consortium effort that we've been involved in. XCMS XCMS Online currently has 50,000 plus registered users. It's a bit of an exaggerated number simply because there's a lot of redundancy there. A lot of individuals create multiple accounts, but just to get more space on our servers. But regardless to say, we do have a fair number of users and new users coming in on a daily basis. Basically, the functions that we're all familiar with is align the data to statistical assessment and ultimately identify the molecules that we're observing. So there'll be essentially a new user face. The latest XCMS developments that have been coming out of the Stefan Newman lab will be implemented in this, and also will hopefully be, you'll find that it'll be much more streamlined analysis. However, what I wanted to say about this was that everybody does have their own version of how to do this sort of analysis now. Shuzhao mentioned his Asari, and Jeff has his own version for processing the data now. So and probably many members of the consortium have their own version. So I think the data processing has really become somewhat of a streamlined approach in itself, and our primary and the whole process is getting easier and I think more accurate as time goes on. Which one is the best is really up for debate, and my focus has been instead to try to get XCMS into gradually get it as good as we can possibly make it, but with an additional focus on using it to identify metabolites. So one of the major efforts that we're putting towards this is integrating XCMS with our Metlin 860, now it's 867,000 molecular standard database. And when I say 867,000, that's 867,000 molecules that we've analyzed and generated tandem mass spectrometry data on for each of these molecules at multiple collision energies and both positive and negative ionization modes. So our real effort right now is we're continuing to grow Metlin, but also the primary effort is to integrate XCMS and Metlin in a more seamless sort of way. And so you might say, oops. And obviously the motivation for this is obvious. I mean, we start off with M over Z values, and that allows you to get the initial potential identifications. However, there's a lot of elemental composition redundancy with respect to that, and that's what led us to the MS2 generation of Metlin. And one of the major problems we had in terms of dealing with the size of Metlin to create a matrix that would represent all the fragments that we're creating in this and for the scoring algorithms. That's odd. Is somebody, looks like somebody's drawing on the slide. So now it typically took using our conventional high-speed computer about 80 days to do this processing. And since we wanted to do this processing multiple times because we wanted to optimize the process, it really was a inconvenient approach to doing this sort of analysis or matrix generation. Fortunately, Scripps has multiple parallelized data centers or clusters that allowed us to actually facilitate these analyses. So now we can actually do it in a couple of days, and it's allowing us to optimize the process much more rapidly. And you'll get a sense of why we wanted to optimize this in a few seconds. So again, the primary motivation for doing this sort of analysis is just to generate a matrix that would allow us to do MS2 scoring in as accurate way as possible against a large number of molecules. However, one thing that we've realized is that MS2 scoring in itself is highly inadequate. And I'll give you an example, a kind of an extreme example of why it's inaccurate in the next few slides. One of the things that we've implemented now is, and this is something that's going to be a part of the XCMS program, is a new version of Metlin. And this new version of Metlin was facilitated by a supplement from the consortium in this last year. And what the supplement was funded to do was convert MS2 data to neutral loss data. So basically this 867,000 molecular standard database where we have MS2 data, we've converted it to neutral loss spectra as well. And for those of you who don't think about these things very often, here's MS2 data, and here's the neutral loss data. So basically the molecular ion is the 203, and the 158 is the first fragment. And basically what we're seeing here is the neutral loss of 45, which is represented by that. And then the 203 minus 116 is the 87 and so on. Now, what struck me when we first started generating this was that neutral loss is extreme. It's been around, people have been using it for decades, and there's thousands of papers on neutral loss type data. But what struck me about it was that there were no libraries like this, no databases like this that could be used to facilitate the identification of knowns and unknowns. And I'll give you an example of why I personally think this is kind of confounding, why this hasn't been generated previously. So here's a molecule. This is rosustatin. It's a drug, and this is the desmethyl version. So the only difference between these molecules is this, instead of having a proton here, you have a methyl group here. But when you look at if you're doing MS scoring on this molecule, the hit is actually extremely poor. I mean, the similarity you would never guess these molecules were as similar as they are based on the MS-MS data. However, if you look at the neutral loss spectra, the similarity, and again, this is an extreme example. This does not happen all the time between very similar molecules, but it does give you a sense of how powerful neutral loss type data can be in assessing the identification or the identification of similar molecules. So with that being said, we've in this algorithm that was funded by the consortium, that is now freely available, and it's described in the JASMAS 2022 paper that just came out a couple of months ago. So what's currently available on Metlin site is the MS2 scoring, which allows you to, again, do similarity analysis or identifications with just MS2 data, which is what we normally expect these programs to do. We are also in beta testing right now with the neutral loss comparative analysis. So these are two separate scoring algorithms that are on our current version of the program. And the final one that is going to be implemented is the MS2NL, which is a combination scoring approach that combines the MS2 data and the neutral loss data. So with that, I'd just like to, again, the primary objective that we in our lab right now is to more fully integrate the XCMS technology and the Metlin technology to facilitate the identification process, which could also facilitate pathway analyses that MummyChog allows you to accurately assess in terms of these untargeted metabolomic data sets. And with that, I just want to acknowledge Martin Kiera, Enrico Dirks, and Aries Porner, who have been very much involved in the integration process, and Aries, again, and Winnie, who have been largely responsible for the size of Metlin as it is right now. And of course, I'd like to, there's lots of individuals or companies that have facilitated the progress and the growth of Metlin. One of them is very recent, has been Cayman, and this just gives you a sense for the types of shipments that they're sending us of molecules. These are all, each of these packages have, in some cases, 20 or 30 molecules in them. So it's really very generous for Cayman to be providing us with this. So I think we've used up pretty much all of our time. So thank you for your attention.
Thank you, Gary, and thanks for the whole team for this presentation. We do have time for a couple of questions. Gary, I do have one. Whenever I see you present on Metlin and the XCMS work, I'm struck by how old things become new again, and how in proteomics, where I have a little more experience, we jettisoned all these very interesting experiments one can do with a mass spectrometer in favor of trying to just get the highest sensitivity we possibly could. And it seems like in metabolomics, we're rethinking that approach and realizing how much information there is in these alternative experimental designs. And I just wondered about your thoughts on that sort of basic question here.
Yeah, so yeah, it's a great question, because I think what you're referring to is the neutral loss. I mean, neutral loss has been around for decades, and and the information within it has really been, it's very much a different dimension than the MS2 data. And taking data that's just sitting right in front of us and using it in a way that could facilitate the unknown identification, or facilitating things that we haven't even thought of yet, I just think is it's really fascinating. And I think it's, again, like you said, Doug, I mean, these things are right in front of us, and there's no reason not to take advantage of them. I as you've probably sensed, I was quite surprised when I started looking up neutral loss databases and couldn't find any that existed.
I think it's a good lesson, and sensitivity not being the only parameter we should be considering. got a question from Tim. And Mamachag, for those ions that don't match the endogenous pathways, is there a plan to push those for identification as potential exposome metabolites? Secondarily, how well do you integrate lipid metabolism in?
Thanks, Tim, for the question. So for lipid metabolism, so we are integrating pathways and ontology from lipid map. So that will be in Mamachag version 3. For the unmatched compound, that's the plan for version 4. But we are playing with a few algorithms how to predict reactions, and we are doing actually a lot of work both on computers and in the lab to push that forward. But I will be very happy to work with you if you have good application cases.
Any additional questions?